In this video I'm going to show you how to determine the electron pair arrangement and the shape of a molecule from its Lewis structure. Shown here on the screen are the possible combinations of electron pairs and lone pairs and the resulting shapes for the molecule. So for instance, if you have a molecule with 3 electron pairs total, that means 3 total lone pairs, bonding pairs, and or double bonds and triple bonds. Those all count the same with respect to counting up electron pairs. 3 results in a trigonal planar arrangement of those. If one of those happens to be a lone pair, then the shape ends up being bent. So this table allows you to determine the end shape for given combinations of electron pairs and lone pairs. I have a procedure that I like to use in determining the shape of a molecule, which starts with just determining the what I call the electron pair geometry. In other words, classifying a molecule into one of those 5 geometries based on the number of electron pairs. And once I have it classified, then I determine the shape based on the number of lone pairs. So we're going to use an example from 3 molecules: methane, ammonia, and water. And what we're going to see is that these molecules all have the exact same electron pair arrangement, tetrahedral, but their shapes end up being different due to the fact that they have different numbers of lone pairs. So the first step in this process of determining the shape of a molecule is to draw the Lewis structure. You need to know the Lewis structure. For methane, we have a carbon surrounded by 4 hydrogens. Electron count: carbon has 4 electrons, 4 hydrogens have 4 valence electrons total to donate. That's 8 valence electrons. We connect those via 2 electron bonds into this skeleton structure. That uses up our 8, in fact. So we have 0 electrons left. So this Lewis structure is done. You see we have a duet on each hydrogen, octet on the carbon. Now, the second step is to determine the electron pair geometry. So if we look at our table, right, we have 2 through 6. The molecule with carbon as a central atom has 4 electron pairs around the central atom, 4, and they're all bonds, 4 bonds. So under electron pair geometry, we have tetrahedral, right? And so I'm just going to draw that arrangement, same as is shown in the table. And you should practice drawing this arrangement. 2 lines, one up, one to the right and slightly down, a wedge coming out slightly to the left, and then a dashed line going back. And that's intended to give it a 3-dimensional look. Now we're going to fill in the atoms around the structure. If we had lone pairs, we would fill those in too. We don't in this case. So we have 4 electron pairs. They are all bonds. Fill in the atoms around our tetrahedral geometry, and there we have the final molecule. And of course, now I assign it to one of the given shapes from the table. Okay, and this is tetrahedral, 0 lone pairs. And I'll use the abbreviation T sub D. So that's for methane. So it has an electron pair geometry of tetrahedral, no lone pairs, and therefore a shape that's also tetrahedral. Let's go on to the next example, ammonia. Ammonia has this arrangement: hydrogens around nitrogen. Nitrogen has 5 electrons in its valence shell. 3 hydrogens each donate 1, so that's 3 electrons, 8 electrons total. We connect to complete our skeleton structure. And in doing so, we use up 6 of our valence electrons. That leaves 2, which go on the nitrogen. So our Lewis structure is complete, so now we're going to determine the electron pair geometry. Well, the counting includes lone pairs and bonding pairs. So there's 4 around nitrogen. That puts it in the tetrahedral group for electron pair geometry. So those electron pairs are going to arrange themselves to be 109.5 degrees apart because that's the furthest away they can get. So 3, I'm going to draw that geometry out. So draw the tetrahedral arrangement. So the same as the steps so far are the same as we've done before. I'm going to draw the exact same arrangement. Now, in this case, though, one of those positions is going to be occupied by a lone pair. But what this allows is you to go through the steps in a very regular fashion, sort of, step by step. And for me, the end result, how the electrons are and atoms are arranged, helps me determine or remember what the name of the shape is. So when I add in atoms and lone pairs in this case, I have 3 hydrogens. One of the positions has a lone pair. And so this molecule looks like a pyramid, sort of, with a trigonal base. That helps me remember what the name of the final shape is. And so the last step, assign the shape, and this one is trigonal pyramid. 4 electron pairs and 1 lone pair. Okay, let's go on to the next example. Water. Okay, H2O has oxygen connected to 2 hydrogens. The electron count, 6 electrons in the valence shell of oxygen, 2 hydrogens, so 2 electrons, that's 8. We finish our skeleton structure by connecting the oxygen hydrogens. That uses up 4 electrons. That leaves us with 4 valence electrons to distribute in the structure. Those must go around oxygen as lone pairs. So now we're going to count, and lone pairs count, so 4, again, no surprise there, because I told you ahead of time that would be the case. But just, we're seeing here how the, when you count your electron pairs to determine the arrangement of those pairs, the geometry, you count lone pairs and bonds. If those were double bonds, they would still only count once, same as single bonds. Okay, so now we're in the tetrahedral geometry. We have 4. I just draw that geometry, and now I'm going to fill in the atoms and lone pairs. 2 hydrogens, 2 lone pairs. It doesn't matter where you put them in this case. So those lone pairs of electrons, negative charge, occupy space, and that's going to prevent the hydrogens from moving into a linear position. It keeps it restricted to this tetrahedral arrangement of all the electron pairs. Of course, the final shape is determined by the positions of the atoms. We don't count the electron pairs in determining sort of what we name the shape. And in this case, the atoms form sort of a bent structure. And that's the name of the shape, bent. Bent with 109.5 degree bond angle approximately. Okay, so let's review this quickly. We had 3 molecules. Each of these molecules had the same electron pair, number of electron pairs, which is 4. And therefore they had the same electron pair geometry, the same starting point, which is tetrahedral. But of course each one had a different set or number of lone pairs. 0 lone pairs for the methane, and therefore its shape is the same, tetrahedral. The 1 lone pair in the ammonia occupies one of the positions in our tetrahedral arrangement, and the final shape is called trigonal pyramid. And then finally, the water with 2 lone pairs in the in the 2 bonding pairs in the tetrahedral arrangement results in a bent shape. So 3 molecules, same number of electron pairs, same electron pair geometry, 3 different shapes.